All right, so quiz today. Um, we had 12 review problems last night, just kind of touching up on some of the material that we've been working on this week, limits and how they relate to continuity. So, first four problems, we're writing what we call extended functions. It's where you find any removable discontinuities and repair them basically by plugging the holes. Remember, holes create removable discontinuities, so if you can plug that hole, it bridges the function. You can't do that with other discontinuities, jump discontinuities, and infinite discontinuities. If you try to repair a single hole, it's a single point's not going to fix anything. There's too big of a gap. What I can tell you is on these types of problems, if you're not ready to factor, then you're going to struggle. So you really got to be ready to factor on these. Both last semester in trigonometry, this semester earlier in Math Now, we devoted an entire day to reviewing the four big methods of factoring, and they certainly tend to pop up a lot of them. So like on this one, you have difference of cubes on top, so x minus 5, right, would be the cube root of x cubed in 125, and then the formula would be the first thing squared plus the two terms multiplied plus the last thing squared. So hopefully you haven't totally forgotten your factoring. The bottom is just difference of squares. And so what we find when we get done is that we have a hole at 5, x equals 5. That's the ones that cancel create holes, and those are removable discontinuities, right? On the other hand, the negative 5, x equals negative 5, does not cancel, and so that creates a vertical asymptote, which creates an infinite discontinuity. There's no way to fix that. So that's just going to be part of the function. There's no way of repairing that. Now remember the formula here. What we're going to do is we're going to take the original function, and that is going to be the first part of the piecewise function, because that's good almost everywhere. Okay, so we'll use that everywhere except where we found that removable discontinuity, which was at 5. So not at 5. Now technically we can't really use it at negative 5 either, but like I said, there's no way to fix that. Now the one question is, what are we going to do at 5? Well, we need to find the height of that hole, and that's going to plug the function and fix that removable discontinuity. How did we find the y value of holes earlier in the semester? Well, when we did rational functions, we knew that holes existed at points, and by factoring, we found the x value. What we had to do is we had to go to the reduced equation, right, to find the y value. So that's going to be 5 squared plus 5 times 5 plus 25 over 5 plus 5. So 25 plus 25 plus 25 is 75 over 10. So that you could either write that, I mean, most people would probably just call it 7.5, but you could also reduce that all the way down to 15 halves. Okay. Either one of those would be an answer. Now, if this was like a you plug the problem into the Google quiz, we would probably make sure both of those were possible solutions. But don't get fancy with the way that on the short answer Google quiz problems, because we have to put in every possible answer that it will accept, basically. And so we try to think of every variation that a student might put in. But if you do something really weird, it's not going to be there, and you may get a right answer and still get marked wrong. So just play it conservative. Don't put spaces between things, those kinds of things. All right, let's jump to number 2. So number 2 looks like we're going to be factoring by perfect squares again in the denominator. So x minus 3, x plus 3. But what about the top? I mean, it's 4 terms, so we're not going to do difference of cubes, difference of squares, sum of cubes, trinomials, and the binomial. You may look for grouping, right? We can take an x squared out of here and here, but these don't both have x's, and there's really no constants that go into everything. So we're kind of stuck until we think of synthetic division, okay? And, at first you're like, well, that's great. I know how to do synthetic division. I know how to do the 1 and the -4 and the -11 and the 30. But what the heck number am I supposed to do, right? Well, don't freak out. There's only 2 possibilities. Remember, we can only remove poles. We can only remove removable discontinuities. And there's only 2 of them. There's only 3 or -3. So you could pick one and try factoring it out, and if it doesn't work, it has to be the other one. Now, this is supposed to be a non-calculator test, but of course, in your situation, it's not going to be the case. And so what you could do is you could graph it, and you could say, well, over here at -3, the graph seems to be fine. Well, that means it's really not fine, doesn't it? That means there's got to be a hole there. Because we know that 3 and -3 can't be okay. You can never have zeros in the denominator no matter what. Now over here at 3, it sure as hell looks like we have a vertical asymptote. So it looks like -3 is the one that is causing our issues. And so that's a way that you could figure out, what was going on. So even if you didn't do that, though, I mean, worst case scenario, you waste, less than a minute trying to divide something out. It doesn't divide evenly, and then you move on with life and try the other one. There's only 2 possibilities. So these problems are not worth freaking out about at all. So we're going to add, multiply, add, multiply, add, multiply, and sure enough, we were right. That has to be a hole there because it evenly, divided out. So what did we do? We divided out an x plus 3, right? That's the -3 root. And what it left was x squared, that's the 1, minus 7x plus 10. So the original function is good to go everywhere except, it's getting a little bit crowded here, isn't it? Everywhere except for -3. So x not equal to -3. We're okay using this, okay? Now, what if x is equal to -3? That's where we have to plug that hole. So really all I need here, I'm going to go ahead and erase most of this. Don't need those x plus 3's, do we? Those are gone now. So really all that's left is this part of the function. And I'm just going to plug in the values down below. So we're talking about plugging a -3 into x squared minus 7x plus 10. That's the remaining part of the function after the x plus 3's cancel over -3 and -3. So we're going to get 9 plus 21 plus 10. So that's 40 over -6. So -46, that reduces to 20 over 3, right? So -20/3. All right. So that's kind of how you're doing these. And I'll go ahead and bust through these next 2 for you just for the sake of making sure you're feeling good about that. All right, so here this time we have, it looks like sum of cubes. So we're going to go x plus 3 And then x squared minus 3x plus 9. Remember, these two guys always are going to be opposites of each other in those formulas. And then on the bottom, we have a trinomial that's being factored into two binomials, and it looks like we're going to, you can kind of cheat with the top, right? I mean, if we're trying to repair a removable discontinuity, there's got to be a hole. And if there's a hole, there's got to be a canceling factor. And the only canceling factor here, it's not going to be the trinomial, it's going to be the binomial. You kind of know it has to be an x plus 3. So you can kind of get hints on what you should be using, okay? So the other factor would be x plus 2. So sure enough, there's your hole at, x equals -3. So x cannot be -3 in the first part of this extended functions, piecewise function, right? The first part of it is just the original function where we're not going to have that hole because we're not going to use that function where the hole exists at -3. So the question then comes down to, what's the height of the hole? And this is just where you got to use the remaining part of the function, right? The reduced function, I guess is what we call it, and plug in that value. So -3 squared minus 3 times -3 plus 9. There shouldn't be an x there. Sorry, that was a typo. Over -3 minus 2. So what do we get? 9 plus 9 plus 9. So 27 over -5. I would just put it in like that. That doesn't reduce. So I think that would be good. And then here we go. On this one. All right, so the top, once again, the bottom is just going to be difference of squares, x minus 1, x plus 1. The top, though, is 4 terms again. So the first thing I do is look for grouping, but I don't see any grouping that's going to work. So it looks like we're going to have to do synthetic division again. Let's just try one. I usually try the positive one first. Now, like I said, you could put this into your graphing calculator and really take a peek at it. And maybe when you're taking a really long time on a quiz, like you have under these circumstances, you can do that. But I think it's quicker just to try one of these with the synthetic division, and if it doesn't work, the other one has to be the answer. So multiply, add, multiply, add, multiply. So that didn't work. That did not zero out. So let's try -1. Multiply, add, multiply, add, multiply, or add, multiply. There we go. So it was -1 again after all. So let's go ahead and get rid of the synthetic division so that we now know, although I guess I shouldn't have done that because I need my factors first. So let's do that. So we now know that the factor is x minus or x plus 1 for the -1 root, and what's left over is what I needed. X squared minus 10x plus 21. That comes from right there. Okay. Some people will factor that, which is fine if you want to, but it doesn't. It's not necessary because we're just going to plug in anyway. So whether you plug your value into a factored equation or not, it's not going to make a difference one way or the other. So we've got ourselves the original equation as long as x is not equal to -1. But if x is equal to -1, we need to figure out what the value of that hole is so that we can repair it, right? So let's do that. And that's just where you plug in and finish off. So -1 goes in, and we get -1 squared minus 10 times -1 plus 21 over -1 minus 1. So that's going to be 1 plus 10. 1 plus 10 plus 21. So that's 32 over -2. 32 over -2, so -16. And now we're done. So think of it, to do these problems, we used factoring trinomials and binomials, factoring perfect squares, factoring sum and difference of perfect cubes, and we even did some synthetic factoring, some synthetic division. So the only factorings we didn't use on these problems were factoring by grouping and factoring out a common term. So a lot of factoring going on. Keep that in mind. All right, 5 through 9, we're just analyzing our graph over here. So let's jump into this. Where does a limit not exist? For a limit to exist, if you go back to Unit 1, 2.1, when we defined a limit, for a limit to exist, the left limit has to exist, the right limit has to exist, and they have to be equal to the same value. We basically have to have the left side of the graph and the right side of the graph approaching the same height. So what's going to prevent that from happening is really just two main things that we've seen, and that is jump discontinuities and infinite discontinuities. Those are the two times when we come in from different sides, right, from the left, from the right, and are not approaching the same height. Now, it would be a problem with oscillating discontinuities too, but we aren't really dealing with those. So we're cruising along here. Everything's continuous, so we don't worry about it at all. Now, we hit a hole here, so this is a removable discontinuity. But if I came in from the other side, we'd still be approaching whatever height this is, the same height. So that limit still exists there. Now, when I finally get up here, we have that jump discontinuity. And so that is a problem. The limit's not going to exist because it looks like the left limit is 7, and the right limit is, I guess that's 4 over here, okay? And then after that, everything's continuous until the end of the interval. So it looks to me like the only place where the limit does not exist is at x equals c, okay? Where is the graph discontinuous? Well, definitely at x equals c because of that jump discontinuity, but we also had a removable discontinuity at x equals b. So x equals b, we have a removable discontinuity, x equals c, we have a jump discontinuity. Which of the discontinuities are removable? Well, the discontinuity at x equals b, because it was created by a hole, is removable. In fact, that's the name of it, right? A removable discontinuity. All right, I think you guys get the point. Let's not cover up our graph. We're not done yet. Number 8, what 2 criteria must be met for a function to be continuous? So this is, a couple days ago, my attendance question for you is, how would you describe continuity? And a lot of you guys kind of went back to chapter 1 and used just the intuitive, well, you have to keep your pencil on the paper kind of idea. But we're beyond that now. You've got to understand this in terms of mathematics. And there's 2 main things that have to happen, okay? The first thing is that the limit of your function, Sx, approaches a specific value, whether it's a, b, c, or d. They're going to ask us about b, so let's just say we're approaching b, okay? Must exist. Okay, must exist. So what that means is as I approach b, I have to be coming into the same height in both directions, okay? Now the second thing that has to happen is that the function's value at b must exist. So it can't be undefined at b and be equal to the limit as we were approaching b. So the limit has to exist and has to be equal to the function's value at b. So the function can't be undefined at b. All right, those are the 2 things that have to happen. The limit must exist and the function's value has to be equal to the limit. That's if you really break down the definition. And I'll go ahead and simplify that definition for you right now. This is what it is. It is the limit, and in our book, they actually use c, x approaches c, but I can use b, has to be equal to f of b. That's the definition of continuity, and it says those 2 things. The limit exists and is equal to the function's value. So why isn't the function continuous at b? Well, the first part of our issue is met because look, the left limit is approaching, I think this is 7, so we'll call it 7. It's 7. The right limit, as we approach b from the right, the y values are approaching 7. But there's a hole there, and the function defines f of b as being equal to 1. So why isn't f continuous at b? It says consider these two requirements, right? So, I mean, if it tells you to use something, then always use that. So a really good answer, I think, would be f is not continuous at x equals b because the limit of f of x as x approaches b is equal to 7, but f of b is equal to 1, and clearly 7 is not equal to 1. And then if you wanted to finish it up, you could say, so limit of as x goes to b of f of x is not equal to f of b. This is the definition of continuity, and look, we said it didn't pass. We said it's not equal. And of course, these are on the back, so I'm sure you've already checked them, but here's all the answers, and here's exactly what we, there's those two criteria we talked about. The limit must exist and be equal to the function's value. And why isn't it equal? Well, here it is right here. Maybe I miscounted because this says it was 6. I was saying using 7, but the same idea, right? All right, let's go to problem 11. Oh, I guess problem 10. Problem 10, name the 4 types of discontinuities. This, you could have just gone to your workbook. This was page, I think, 10 or something in your course pack, and it just reviewed the types of discontinuities. You've got your removable discontinuity here with the hole. You got your jump discontinuity here. You got your infinite discontinuity with the vertical asymptote. And then the one that we're not going to really make you analyze is the oscillating discontinuity, the kind of crazy one, okay? I certainly appreciate that you're like, yeah, but what about the tactilian discontinuity? And I just want to be very clear on that. That one was not real. Rah! So keep that in mind. Number 11, locate all discontinuities for this graph. So here's the work. I actually have it worked out here, so I guess this will go a little bit faster. So we've got to factor the top. Now notice the first thing I do in the top is I factor out a common x. So that's one of the, factoring out a common term. That's yet another form of factoring. So now we've used 4 out of our 5 major forms of factoring. I think the only one we haven't done is by grouping. You really have to be able to factor all 5 ways to be successful with these types of problems. Then we can factor the top into into 2 binomials, and the bottom factors into 2 binomials because it's difference of squares, and we can see that there are 2 values that are not good. And those 2 values, which are problems, are x equals 4 and x equals -4. And the problem at x equals 4 cancels, so that makes it a hole. So that's going to become a removable discontinuity. And the other one becomes a vertical asymptote. So that's going to become an infinite discontinuity. Notice that holes and vertical asymptotes are not types of discontinuities. They cause types of discontinuities. Holes cause removable discontinuities. Vertical asymptotes cause infinite discontinuities. But the answer is right here in front of us, so I guess we don't need to worry about this one anymore. Last problem, number 12. I love these, but we're not going to be able to really ask you to do these the way that we normally would because you can't really graph on Google Quiz. So we may have like a picture and you have to analyze it, but let's break these down. The first thing that happens is we come to the 4. Okay, we come to 4. And the first thing they tell us is that 4 exists. okay, f of 4 exists. Think about what that means regarding the four possibilities, because right now, really, the four possibilities are that the function is continuous at 4, there's a removable discontinuity at 4, there's an infinite discontinuity at 4, there's a jump discontinuity at 4. We're not going to give you the oscillating discontinuities. So the fact that 4 exists tells me it can't be a, see if I can, there we go, that'll work. It tells me it can't be an infinite discontinuity, because infinite discontinuities have vertical asymptotes where the function is totally undefined at that value and just going up and down, but the x can never equal anything there. So that one's out, okay? Now let's talk about the next thing it tells us, which is that the limit, as I come in from, and there's a little negative sign there, so as I come in from the left, is equal to f of 4. Okay, so that's telling me that, you know, my graph's coming in to the actual value of the function. Okay, so we knew f of 4 existed somewhere. Now it's telling me I'm actually coming into that value. So I guess if I wanted to break it down in, you know, chronologically here, I would say, all right, f of 4 exists. I don't know where, but I'm going to say right here, right? And now the second part here tells me that my function actually approaches that value from the left. But, okay, but it's not continuous. So as soon as they tell me it's not continuous, that takes care of continuity. It can't be continuous, okay? Could it be a removable discontinuity? Could it be a jump discontinuity? I think it could not be a removable discontinuity, because if it was a removable discontinuity, both sides of your function, okay, both sides of your function would approach the same height. Well, we already know that the left side of this limit is approaching a closed point, but with a removable discontinuity, both sides would have to approach an open point, so that's impossible. So all that's left is a jump. So this second value could not be also closed, because then it wouldn't be a function, right? We already have one closed point, and then you just go off. So that's any kind of graph that you did that looked like that would be good. And there's, you know, everybody could draw different pictures. As long as you had those conditions, you would be good. But you have basically 1, 2, 3 clues, and those clues help you eliminate these possibilities. And so that's kind of the way that you go through a problem like this. Hopefully this helped shake out some of the last questions before the quiz, which we'll do it kind of like we have been, posting it probably around 11 and leaving it open until about 4, so you have a 5-hour window. And let me, you know, if you have any last minute questions in the next couple hours before I post it at 11, feel free to shoot me a quick email, and I'll try to clear up any last questions. Have a good weekend, and we're getting so close to calculus. Calculus is coming up on Wednesday next week. I hope that you're excited. Have a good one.